Today we are going to present our project, Benchmark Comparison of Time Series Algorithms on Multivariate Brain Data. Machine learning works best on datasets that contain hundreds or more instances of data. Datasets produced through FNIRS technology often define what is ideal for machine learning. It is not uncommon to have less than 10 instances of an event per participant. The data are often noisy as well. Existing machine learning algorithms need to be customized for time series data. One difficulty with time series is that many algorithms would split up the data within a period of time and learn off of it separately, whereas time series data is dependent on the preceding data, and thus, when split up, correlation between data points is lost. Another challenge is that customized algorithms for time series data are developed for univariate data. Therefore, it is necessary to transform the multivariate data to univariate, though the process causes a loss of information from the dataset.
We propose to evaluate and benchmark existing open-source machine learning methods designed for time series data for their use on FNIRS data. As a benchmark, we will use a curated EEG dataset that has an established use in assessing machine learning algorithms. Then, we will extend our application of these methods to a dataset from ongoing FNIRS research. We will measure the success of each algorithm based on accuracy, time efficiency, performance on various sizes of data, and interpretability. Our results will aid brain-computer interface researchers with analysis of existing methods applied to FNIRS.
We selected 4 algorithms from the Python library skTime that focuses on developing algorithms for time series datasets. We chose algorithms that would cover a variety of machine learning methods. Time series forest classifier implements classic forest machine learning methods specifically on time series datasets and uses a combination of entropy gain and distance measure for evaluating the splits. Master SQL uses logistic regression with extracted features from a variety of symbolic representations through the use of SQL. Bus Ensemble extracts words out of the time series dataset to build features that represent the frequency of each word. KNN is an adapted version of the scikit-learn KNN classifier. All of these algorithms were specifically designed for univariate data and modifications to the data needed to be made to process a multivariate dataset. In time series forest classifier, number of estimators represent a number of trees in the forest, and it is an important parameter affecting efficiency and accuracy. The best accuracy obtained with the algorithm and related efficiencies are as follows. UCI EEG big dataset has the highest accuracy even for small number of trees. This algorithm has higher accuracy on UCI EEG small dataset compared to FNIRS dataset. For varying number of trees in the forest, we evaluate the accuracy and efficiency of time series forest classifier on FNIRS and UCI EEG small dataset in the following plots. The accuracies tend to increase as the number of trees increases, but the change is relatively small and accuracy is already good for almost all of the number of trees. And as we expect, increasing number of trees result in increasing runtime of the algorithm, but generally TSF seems to be an efficient time series classifier.
Mr. SQL is very efficient in terms of the time taken, but performs poorly when it comes to accuracy. The algorithm takes 3 parameters: SQL mode, symbolic representation, and custom configurations. For our datasets, the CLF SQL mode, which uses Mr. SQL as an ensemble of SQL modes, was used, and the symbolic representation was SAX. Out of the 3 experiments, the best accuracy was achieved with the FNIRS dataset on an 80-20 train test split. While it took the maximum amount of time for the UCI big dataset, it gave the least accuracy for the scenario. The results show that Mr. SQL is probably more suited for binary classification as opposed to multi-class classification, since it performed much better on the FNIRS dataset and not so well on the UCI datasets.
Bus Ensemble is the longest running algorithm from the 4 selected, with approximately a 2-hour runtime on the large UCI dataset. For the large UCI dataset, the best accuracy was from the default parameters given by skTime. The small dataset had the average accuracy among all of the algorithms and still took a larger amount of time. It had the best accuracy on the 80-20 train test split with a minimum window of 24 and a threshold of 92%. The threshold is the default for skTime. The FNIRS dataset took approximately a minute to run and was the fastest and is the smallest of our datasets. Had the best accuracy from all 3 datasets at 77.38% with the minimum window set to 10 data points and the threshold set to 84% accuracy. The minimum window here is the same as skTime's default, but the threshold accuracy is 8% lower than their default. Finally, the best trained test split was not 80-20 with the FNIRS, which could be due to the small size of the dataset, resulting in very few samples in the test set when it contains only 20% of the data. Here are the graphics depicting the tuning performed on FNIRS and small UCI EEG datasets. The two figures show the train and test splits that produce the best results, and the arrow on each graph indicates the highest accuracy given these parameters from the previous slide. On average, FNIRS has a better accuracy across all parameters than the UCI dataset.
K-nearest neighbors is the fastest running algorithm from the 4 algorithms selected, with a runtime around 1 second or less for the large UCI dataset. In the large UCI dataset, the best accuracy was from the default distance metric given by SK-time and a K-value of 1. This accuracy was very high at 99.8%, and even when the K parameter was varied, it remained in the 90s, indicating that KNN performs generally very well with large amounts of data. In the small UCI dataset, KNN was very efficient, and the best accuracy was 93.5% with a 70-30 training test split and a K value of 1. On the FNIRS dataset, the best accuracy was achieved at 65.58%, with the default SK-time distance metric and a K equal to 1. The best trained test split was also 70-30. Over many trials in KNN, the small UCI and FNIRS datasets seemed to both perform well on this split, which might be due to their medium and small sizes requiring a few more test examples than the 80-20 split afforded. Amongst all three figures, there is a clear trend that K equal to 1 produces the best accuracy. On the FNIRS data, there was some small amount of fluctuation in the accuracy based on the K value, with an overall decreasing trend. In the UCI datasets, there was a very clear linear trend that as K increased, the accuracy decreased. Overall, this indicates that starting with the parameter of K equals 1 is recommended, and KNN performs generally well.
The results we found for proximity forest were inconclusive, with scores centering around barely better than random. We struggled to find an environment on which to run this algorithm and ended up reducing the number of estimators and maximum depths to significantly lower than those of the default setting. Unfortunately, this left us unable to compare the algorithm with others analyzed. Details on the limitations of this particular algorithm will be included on our website. Based upon our results, we would suggest KNN as the best algorithm for generic classification on neuroimaging data. It is fast, has high accuracies on the larger data sets, and better than chance accuracy on the FNIRS dataset. It is a well-known algorithm that most beginning computer scientists would be familiar with. KNN would be a good place to start analyzing a dataset before moving on to other algorithms such as TSF or BOSS. TSF had similar accuracies as KNN, but stopped performing as well on the FNIRS dataset and has a longer runtime. BOSS Ensemble has the best accuracy for the FNIRS data. However, it is the most inefficient algorithm. Its worst performance was 2 hours on the UCI large data set, and even on the FNIRS data set, it took over a minute to finish fitting the model, while the other 4 algorithms took less than a minute. We would not recommend Mr. SQL for neuroimaging classification. Despite the speed that the algorithm performs at, it had the worst classification accuracy for each of the data sets,